Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. My name is Muhammad Zaid Khair bin Muhammad Kasim. My ID is 2020611732 and my supervisor is Dr. Muhammad Nur Azmi bin Abdul Pattar. Today I'm going to present about my FYP proposal and my title is Customized Design and Additive Manufacturing of Actuated Ankle Foot Orthosis. I plan my project activities by using Gantt chart method, and this is my project activities for this semester and the next semester. A4 is a piece of equipment worn on the foot and lower leg that supports and stabilizes the ankle. It is frequently used to make walking easier for those with mobility issues. The objective of this project would be to develop an AFO that is adapted to the unique requirements of each user by using customized design and additive manufacturing methods. This can entail developing a 3D model of the AFO using computer-aided design (CAD) software and producing the finished item using additive manufacturing processes like 3D printing. Complex, personalized products may be made with high accuracy and precision with additive manufacturing. It also has the benefit of generating less waste and facilitating quick prototyping and iteration. Developing and producing a personalized AFO that is more effective and pleasant for the user could be feasible. The first highlighted point in literature review for this project is customization of the design. The design of a custom ankle foot orthosis is typically based on a comprehensive evaluation of the patient's specific needs and goals. This evaluation typically includes a physical examination, gait analysis, and other assessment to determine the patient's impairments and functional limitation. Based on the results of the evaluation, the manufacturer will design an AFO that is tailored to the patient's specific needs. Next is additive elements in the manufacturing process. There are several additive elements that can be incorporated into manufacturing of ankle foot orthosis, including 3D printing. This technology allows for the creation of custom fit AFO that are tailored to the patient's specific needs. This can be done using a variety of materials, including plastic, carbon fiber, and advanced polymers. Next, computer-aided design. CAD software can be used to design and manufacture AFO with precise dimensions and shapes. The third is control system of the device. In this project, the hardware design consists of passive elements and stiff or compliant actuators, whereas the main component in the software design is the design of a control algorithm. The purpose of this system is to stabilize the actuated ankle foot orthosis mechanism since the system was subject to an unknown disturbance brought on by ground reaction force and foot weight. Adaptive and backstepping control are both approaches to designing controllers for dynamic system. Both adaptive control and backstepping control can be used in the design of controllers for powered AFO. Next is the improvement of human gait. Human gait is the body's movement pattern as a person walks or runs. It is a complex process that involves the coordination of multiple body segments and joints, including the legs, hips, trunk, and head. Gait is an essential aspect of human movement as it allows individuals to perform activities of daily living, such as walking and running, and navigate different environments. It is also important in physical therapy and rehabilitation, as abnormalities of gait impairments can indicate underlying musculoskeletal and neurological conditions. Several different types of gait patterns can be identified, including normal gait, limb gait, antalgic gait, hemiplegic gait, and ataxic gait. This project's primary focus is to improve a human's normal gait. It is the typical gait pattern seen in individuals with no mobility impairments. And the last point is support for flaccid paretic plantar flexor and dorsiflexor muscles. Flaccid paretic plantar flexor and dorsiflexor muscles are muscles group that are weakened or paralyzed due to neurological damage or disease. Paralysis or weakness of the muscles involved in movement can result in difficulties with specific tasks. For example, plantar flexors are responsible for bending the toes downward and away from the leg. dorsiflexion is responsible for extending them upward toward the leg. Current treatments for chronic foot drop provide dorsiflexion support, but they either impede ankle push off or are unsuitable for all patients. These are the summary table of 20 different journal articles that I have used to perform the literature review. Based on this, I have decided to use PLA for the material of the project, adaptive control for the control system, and series elastic actuator for the actuation system. The first problem statement for this research is the performance of existing actuated ankle foot orthosis that can provide improvement for human gait and support for placid paretic plantar flexor and dorsiflexor muscles at the same time is still in debate among manufacturers. Second, the existing ankle foot orthosis still uses fragile and unreliable materials. And the third is the user's comfort while using the ankle foot orthosis still does not meet the standard requirement for daily use. The objectives for this research is to construct mathematical modeling, simulation, and experimental verification on actuated ankle foot orthosis performance. Next, to optimize the strength analysis of 3D printed ankle foot orthosis using PLA and PLAC. The last one is to develop an actuated ankle foot orthosis that prioritizes the user's comfort without neglecting its durability and reliability. There are several limitations to consider in designing an AFO. These include comfort, durability, range of motion, weight, and effectiveness. Some users may find that AFO are uncomfortable to wear, especially if they are not properly fitted. These devices can be expensive and may need to be replaced over time due to wear and tear. Ankle foot orthosis can limit the range of motion in the foot and ankle, making it more challenging to perform certain activities such as running or climbing stairs. They can be heavy, making them less comfortable to wear for long periods. Ankle foot orthosis may not be effective for all individuals, and the specific benefits of an ankle foot orthosis will depend on the individual's specific condition and needs. This is the methodology of this project. The first phase is literature review. We study the previous research papers regarding ankle foot orthosis, and then we identify the material, design, control system, and actuation mechanism. Then we analyze every component and system. Next is we identify the problem. We compare the advantages and disadvantages of the previous ankle foot orthosis. And then we select the force transmission mechanism and actuation mechanism. Next is we analyze the strength of the material. First, we design the 3D CAD modeling of AFO from PLA and PLAC material by using CATIA V5 software. And then we optimize the strength analysis for both materials by using von Mises stress test and deformation test. And then we select the best material. Next is we develop the control system. We develop the electronic circuit and schematic diagram, and then we compile and upload coding for series elastic actuator, control, and sensors. And then we fabricate an assembly. The first thing is we manufacture the 3D parts of AFO by using 3D printing, and then we assemble the 3D parts with the actuation system. And the last one is AFO assessment and evaluation. We develop of the AFO or actuated ankle foot orthosis, and we analyze its performance. This upcoming slides is the expected results for this project. This is the 3D CAD modeling of the AFO that I have designed by using CATIA V5 software. This design consists of cuff band, hinge mechanism, and footplate. This anthropometric measurement data is from one of the earlier study publication. It is used to design the AFO in CATIA V5. However, only 12 measurements were required for the new AFO design in this study. This is the electronic circuit diagram for the control system. This electronic circuit diagram for a series elastic actuator can vary depending on the specific design and requirements of the AFO. However, the typical circuit for a SEA-based AFO in this project includes a battery to provide the necessary voltage to the circuit, an Arduino Uno R3 serves as the brain of the AFO and controls the operation of the SEA. Next, a force sensor measures the force applied by the SEA, while the tilt sensor measures the angel's rotation of the ankle. Also, a DC motor is used to actuate the SEA. Lastly, the wiring and connectors connect all of the above components and allow them to communicate. The specific design and components of the circuit may vary depending on the specific requirements of the AFO and the goals of the design. This is one of the AFO from the previous study that attached with the series elastic actuator. Examining which AFO performs best in terms of mechanical strength is the goal of the study. A comparison of the behavior deviation of PLAFO and PLACAFO has been made. This study aims to investigate how various materials affect AFO strength following additive manufacturing. FEA simulations were used in the plan to forecast the behavior of both types of AFO to save time and resources. The AFO is subjected to a gravitational acceleration due to a young child's typical weight of 30 kg. The force must be calculated using the formula F equal mg, where m is the child's weight and g is the acceleration of gravity. While maintaining the foot still, the force is assessed on the AFO's leg. Materials are often categorized using force displacement curves. These curves are a result of experimental analysis. Using the first equation, elastic energy may be computed based on the connection between force and displacement. This method of calculating elastic energy has been used to examine how the AFOs deform under stress. The simulation deformation distribution plot and von Mises stress distribution were utilized to compare the experimental findings. Most complicated 3D printed objects have different modulus values than standard samples because the interior geometry is produced by the layering of materials, which makes the structure distinct from the standard samples. The second equation was applied to actual modulus calculations to generate the most accurate prediction and integrated into the simulation process. The equation, which was also applied in the earlier studies on orthosis, was derived from Hooke's law of proportionality. The table is the mechanical properties of both materials. From the table, less elastic energy was displayed by the PLAC base FO, which means less deflection when 160 Newton was applied. The PLAC base FO were stiffer than the PLA base ones since there was less stored energy, which is why they ought to be preferred. The experiment demonstrated that adding carbon fiber to PLA increased its strength and robustness. When testing carbon fiber reinforced thermoplastics to make FO, researchers noticed the same outcomes. Taking into account the fixation of the lower half and the loading at the other end, it helped to improve the correctness of the FA model for this orthosis. The graph is the force displacement curve for both PLA and PLAC. There are several trends that are likely to shape the future of FO. The first is increasing use of lightweight materials. FO are likely to become lighter and more comfortable to wear as manufacturers continue to use lightweight materials such as carbon fiber and advanced polymers. Next is the development of a smart FO. FO that are equipped with sensors and other advanced technologies such as motion sensors and Bluetooth connectivity are likely to become more common. This smart FO will allow for real-time monitoring of gate and other parameters and may even be able to provide feedback to the user to help improve their gate. Next is the customization. As 3D printing technology becomes more widely available and affordable, it is likely that FO will become increasingly customized to the individual needs of the user. This will allow for a better fit and greater comfort. This is the end of my presentation, and thank you very much for this opportunity. Assalamualaikum warahmatullahi wabarakatuh.